In this video, I am going to derive Schrodinger wave equation, which is a basic principle of physics. It is said to basic principle of physics because it cannot be derived from any existing principles of physics. It is even more basic than the Newton's laws of motion because Newton's laws of motion can be derived from Schrodinger wave equation when it is solved on the classical level, while Schrodinger wave equation cannot be derived from the Newton's laws of motion. So it is an important basic principle of physics. We will start its derivation by considering a wave function for a free particle, which can be written as psi equal to a exponential minus iota over h bar et minus px. Here is just a general constant. H bar is the reduced Planck's constant, E is the energy, and P is the momentum of the particle. We will differentiate this equation with respect to x, and our first derivative of this function gives us iota p over h bar times the original wave function psi, and then we will again differentiate it with respect to x, and double derivative of this wave function with respect to x gives us minus p square over h bar square times the original wave function psi. A little simplification to this equation gives us the following equation: p square psi equal to minus h bar square partial square psi over partial x square. We will name this equation as equation 2 and will use it in the later stage. And now we will differentiate the wave function of a free particle, which we named as equation 1 with respect to time, and the differentiation with respect to time gives us minus iota e over h bar times the original wave function psi. A little simplification to this equation gives us the equation of the form E psi is equal to minus h bar over iota partial psi over partial t, and a bit more simplification gives us E psi is equal to iota h bar partial psi over partial t. This is the general form of Schrodinger wave equation, and now it will depend upon the type of energy that the particle may have, and we can write this equation for the particle which have some specific type of energy. For a more general particle, the particle energy is the sum of kinetic energy and its potential energy, that is p square over 2m as its kinetic energy, and potential energy is usually some function of position and time. Multiplying this equation by psi on the both sides, we will have the following form of equation as E psi is equal to p square psi over 2m plus potential energy and the wave function. Using the value of p square psi from equation 2 in this equation, we will get the following form of Schrodinger equation as E psi is equal to minus h bar square over 2m partial square psi over partial x square plus uxt psi. This is the one-dimensional Schrodinger wave equation for a particle who is moving with a kinetic energy p square over 2m and with potential which is some function of position and time. This is one-dimensional Schrodinger wave equation, and we consider it that the particle is moving along the x-axis. Now we can generalize this equation to the 3 dimensions by considering the motion along the other 2 axes, which are y and z axes. And our equation for 3 dimensions becomes equal to E psi is equal to minus h bar square over 2m partial square psi over partial x square plus partial square psi over partial y square plus partial square psi over partial z square plus uxt times some wave function psi. This is the 3-dimensional Schrodinger wave equation for a particle. Thank you for watching this video.